Namaskar friends, I welcome you all in this class of structural analysis. Today we are going to discuss analysis of structures by energy methods. Friends, energy methods are quite important, and from very ancient times energy methods have been used to analyze the structures. These methods are very general in nature, and long back since 4th century BC they have been used. I will give you the concept of strain energy. If any structure which is linearly elastic, it obeys Hooke's law, and if it obeys Hooke's law, then if any force or system of forces are applied to the structure, then the strain energy is stored in the structure because of the axial forces, shear forces, bending moments and twisting moments. And this is because the deformation inside the structure which is elastic in nature. So that's why we call it that energy is stored in the member. So if you say what is the strain energy stored by a member, this is equal to amount of the work done by the external forces to produce the deformation. So friends, we will see one by one that how the strain energy in various structures due to various types of forces are stored. So let us derive strain energy due to axial forces. So friends, suppose this is an element of length say ds, and we are applying axial force say F. On this element. So what will be the energy stored in this element? This will be equal to say the average force F by 2 multiplied by the deformation delta in this element ds. Why we are taking this average force? Because as soon as we start applying force on the element, the elongation starts and the energy is stored. So what happens that the axial force increases from 0 to F for an elongation from 0 to delta. So the work done will be equal to this area, that is the force I can take F by 2 into delta or F multiplied by delta, and its half energy will be stored. Now what is delta here? You know from your classes in strength of material. From strength of material you know that modulus of elasticity E is equal to stress upon strain, and stress is F divided by A, where A is the area of cross section of the member, divided by strain. Strain is delta divided by length of the member. In this case, this is ds. So if you calculate delta from here, delta will be equal to FDS by EA. So if you put this value of delta here in this calculation, so du will be equal to F by 2 multiplied by FDS divided by EA. So this becomes F square ds divided by 2EA. Now if we want to calculate the total strain energy stored in a member due to axial force, then it will be equal to U will be equal to integration from 0 to L F square ds divided by 2EA. Similarly, friends, we can calculate the strain energy stored by a member when shear force is applied. So similarly, as we calculated in the case of axial force, in the case of shear forces, say this is a element of length ds and shear force Q is acting on it, then it will be equal to average shear force, that we will take Q by 2 multiplied by the shear displacement delta, which will be equal to, as you know from your previous lectures on strength of material, that this delta will be equal to Q by 2 multiplied by QDS divided by AR into G. Friends, here AR is the reduced area of cross section. We take AR is reduced area of cross section, and G is the shear modulus of elasticity. So this will become Q squared ds divided by 2ARG. If you want to calculate the total strain energy stored in a structure, then it will be equal to integration from 0 to L for all the members of the structure, integrated on Q squared ds divided by 2ARG. So friends, you can see that you have seen how to calculate strain energy in a structure stored by the axial forces and shear forces. Now we will calculate the strain energy stored in a member by when bending moment is applied. Again you will see here that for bending moment, the moment of inertia of a section of any member is important. Now what will be the energy stored, elemental energy, when bending moment is applied? This will be equal to m by 2, that is average moment force multiplied by angle of rotation, say d theta. So what happens, suppose this is a element member of length, say ds. This is angle d theta, that is the angle of rotation because of the moment, bending moment coming here. Now from simple geometry you know that d theta is equal to ds upon r. R is the radius, this radius. So R is this radius, and from a strength of material you again know that m by I, here I is the moment of inertia of this cross section taken along the neutral axis. M by I is equal to E divided by R. So from here you know that 1 by R is equal to m divided by EI. Now I put this value of 1 by R here in this calculation of d theta. So it will become d theta will become mds divided by EI. Friends, now I will put up this value of d theta here in this equation. So now the strain energy will become m by 2 multiplied by mds upon EI. So this becomes m squared ds divided by 2EI. Now if we want to calculate the strain energy stored in the structure, so U will be equal to integration all along the structure m square ds divided by 2EI. Similarly, we can calculate the strain energy stored by a twisting moment. So what will become here? Here the twisting moment average, we will take the average twisting moment T. So it will be equal to elemental strain energy will be equal to T by 2 multiplied by d theta, the angle by which the element has been twisted, element of length ds has been twisted. Now this will become T by 2 multiplied by TdS by Gk. Friends, here you know in your strength of material class that K is the property of the twisted member depending on its shape, and the values of K can be found from the tables given in your book. So when you want to calculate the total strain energy, it will become the integration of T square ds divided by 2Gk. So suppose if you want to write the equation for the total strain energy stored because of all types of forces in a structural member which is linearly elastic, then what will be the equation? The equation will be strain energy because of the axial forces, that is F square ds divided by 2EA plus strain energy because of the shear forces divided by 2AR into G. You should remember here that in X and Y direction, if the shear forces are coming, then we will have to take and integrate the strain because of the shear forces in both the direction. Again, for bending moment, it will be m square ds divided by 2EI. Here also bending moment may be in different direction, in X and Y direction, both perpendicular directions, so then the values will be taken in both the directions. And again for twisting moment, T square ds divided by twice Gk. Friends, in practice, when we are analyzing a pin jointed structure such as trusses, as you know, these are pin jointed trusses. The joints are pin jointed, and there is only axial forces in such type of members. So there is no bending moment or twisting moment coming on these structures, and shear force also we can neglect. So predominant forces are only axial forces, either compression or tension. So in this case the strain energy will be only this much, F square ds divided by 2EA. So we can consider only axial forces, and we can neglect the other types of the strain energy because of the other types of forces on the structure, because the predominant forces are only axial forces. Similarly, in plane frames and rigid jointed structures, or beams, any plane frame such as this one, or any beam, on these structures only the loading from this side is there in this plane, so there is no twisting moment on these structures. So what we can say, that we can neglect the value of this one, and the strain energy will be equal to F square ds divided by 2EA plus Q square ds divided by 2ARG plus M square ds divided by 2EI. But in such type of structures, if we calculate, you will see that the predominant forces will be the moments. So this will be important, whereas the values of strain energy because of the axial forces and the shear forces are comparably very small in comparison to the values coming because of the bending moment on the structure. So we can neglect these forces, and we can use this formula for all practical purposes in analysis of structures. So friends, as we have seen, we have calculated the value of strain energy in a structure because of the various types of forces. Now we will see that how we are going to use these values of strain energy in analysis of a structure. These are the strain energy due to bending moment. We have calculated it. Then the strain energy due to twisting moment, we have also calculated these values. Now let us see the principle of virtual work. Virtual work is a very important technique, and it was first postulated by Aristotle way back in 4th BC. As the name suggests, it is very simple. It says, what do you understand by virtual work? It means hypothetical work either by real forces with virtual displacements or virtual forces with real displacement. What is the principle of virtual work? So the first principle is principle of virtual displacement. What does it say? It says that the total work done by a rigid body held in equilibrium by a system of forces and reactions on the body during a small virtual displacement is equal to 0. So friends, it may seem to be very redundant to you, but it is very useful method to calculate forces and displacement. So as I explained you that virtual work means that either virtual forces with real displacement or real forces with virtual displacement. So the amount of if a body is in equilibrium and it is a rigid body, then virtual work will be equal to 0. This is the basic principle. So it says in principle of virtual displacement that the total work done by a rigid body held in equilibrium by a system of forces and reactions on the body during a small virtual displacement is equal to 0. From this method we can calculate the values of forces, and unit load method you must have done is based on this principle. Now the principle of virtual forces, and it says that the total work done by a rigid body subjected to deformations compatible with the support conditions held in equilibrium by virtual forces and reactions on the body is equal to 0. Now on the basis of this virtual work, you can derive the Castigliano's theorems. These theorems are also very important, and we can use these theorems to solve determinate as well as indeterminate structures. Let us see what are the Castigliano's theorems. So theorem 1 is the partial derivative of the strain energy of a linearly elastic structure represented in terms of displacements with respect to any displacement delta at coordinate j is equal to the force P at coordinate j. So the things we have to remember in this is that it is a linearly elastic structure, because then only strain energy will be stored, and it is a rigid structure. The objects are rigid, and when we differentiate the strain energy with respect to displacement, then it gives the force. This is the theorem 1. So if any body is there, a rigid body is there, and there are system of forces acting on it, say P1, P2, this is Pj, Pn, and because of this small displacement delta 1, delta 2, delta g, and delta n is coming on the structure. So it says that the partial derivative of strain energy with respect to delta J, that is displacement at any particular point J, will be equal to force applied at that point J. So friends, suppose this is a rigid body and it is in equilibrium, and suppose that you apply a force, say delta Pj, and you allow a displacement here of delta J, a small displacement, keeping other displacement 0. How can we keep other displacement 0? We can keep other displacement 0 by applying certain forces we have to apply at all the places. And if there is no displacement, then strain energy will be stored in this structure. So what will be the value of strain energy? Suppose what will be the work done? Work done will be equal to, here the force Pj is working and we are making displacement delta J. So the strain energy, say du, will be equal to Pj multiplied by delta J. Let us call it delta U. Delta U will be equal to Pj multiplied by delta J. Because the other displacement at other points, we have kept it 0, and the strain energy stored by the body will be equal to the external work done on the body. This will be equal to Pj multiplied by delta J. Why are we taking here Pj as constant and not Pj by 2 as in the earlier cases we were taking? Just because that here Pj has already been applied here and it is in equilibrium. So the total force Pj is acting on the body, and against this force we have done movement delta J. So the work done will be equal to Pj multiplied by delta J. Whereas in the earlier cases we were seeing that the force has been applied from the initial stage, and as the force has been applied at that time the displacement was 0, and gradually we started applying the force. So force were applied from 0 to say a value P or F. So that's why an average force P by 2 was taken. Whereas here Pj was already in equilibrium and the total force was already applied. So the work done will be equal to Pj multiplied by delta J. Now from this equation, delta U by delta J will be equal to Pj, and if we take limit as delta J tends to 0, this will become del U by delta J is equal to Pj. This is the Castigliano's first theorem, that if there are forces, a system of forces are applied on a rigid linearly elastic body, and the forces are, and the body is in equilibrium, then the partial derivative of the strain energy with respect to displacement at any coordinate J will be equal to the force applied at that coordinate J, that is Pj. So this is the Castigliano's first theorem. Friends, we will apply this theorem in the next session and we will solve few examples. Then it will be clear to you that how the Castigliano's theorem is used for analysis of the structures. Now let us see the second theorem. The second theorem says that the partial derivative of the strain energy of a linearly elastic structure represented in terms of forces with respect to any force P at coordinate J is equal to the displacement delta at coordinate J. Friends, you are finding that in brackets here written represented in terms of forces, and in the earlier case you found that it was written represented in terms of displacements. Why it has been written here? Because if you want to differentiate with respect to forces, then you should represent the strain energy in terms of forces, and if you want to differentiate with respect to displacement, then you should represent the strain energy in terms of displacement. So in the earlier cases we were representing the strain energy in terms of displacement, whereas in theorem 2, since we are going to differentiate it with respect to forces, so the strain energy should be represented in terms of forces. So if you see in this theorem 2, the partial derivative of the strain energy of a linearly elastic structure represented in terms of forces with respect to any force P at coordinate J is equal to the displacement delta at coordinate J. So it is just reverse of the theorem 1 what we have. Friends, you can see that theorem 2 this was theorem 1, and theorem 2 is nothing but del U by del Pj is equal to delta J. See, this is the result, which is very simple to remember, because in the first case what we are doing in the theorem 1, in first case, that we are the partial derivative of a strain energy with respect to delta J, that is displacement at any coordinate J, is equal to the force applied at that coordinate J, that is Pj. The reverse of that is also true, that derivative of partial derivative of a strain energy with respect to the force applied at any point Pj will be equal to the displacement at that particular point J, that is equal to delta J. So this is theorem 2, Castigliano's theorem 2. Now friends, I will explain you the minimum energy theorem. That is the last thing I am going to explain in this session, and in the next session we will solve few examples. So what is minimum energy theorem? It says that in any and every case of a statically indeterminate structure where an indefinite number of different values of redundant forces and displacement satisfy the condition of a statical equilibrium, their actual values are those that render the total strain energy stored to a minimum. So this minimum energy theorem comes from the conservation of energy, and obviously the strain energy stored in a system will be minimum, subject to the it should satisfy the statical equilibrium condition and the support conditions of the structure. In most of the cases where support conditions are there and there is no movement, this value of total strain energy will be equal to 0 if we do partial derivation with respect to any force or with respect to any displacement, as the case may be. So we will see in the next session that the Castigliano's theorem can be derived from this minimum energy theorem. So friends, let me summarize this session. In this session we have learned that strain energy is stored in a structure which is in statical equilibrium and which is linearly elastic rigid body, and how to calculate the strain energy because of the various types of forces. We have calculated strain energy because of the axial forces, because of the shear forces, because of the bending moments, and because of the twisting moments. And we have seen that for truss members, pin jointed members, where axial forces are important and predominant, the strain energy because of the axial forces only should be considered for analysis. And for a plane frame or beam where the bending moments are predominant, only the strain energy stored by the bending moment should be considered for ease of calculation, and they are true for a fair degree till a fair degree of accuracy. So in the next session, starting from 1 o'clock, we will solve a few examples based on these principles of strain energy. We have also seen the theorems of Castigliano's theorem and principle of virtual work. We will use these theorems for analyzing indeterminate structures in the next class. Thank you very much.